The third vector n. So, n is by definition is B cross T. It is the cross product of binormal and the unit tangent T. The expression of B and T both are available to me. So, this is r dot cross r double dot, r dot cross r double dot, and then you have T, T is r dot upon mod r dot. So, it becomes mod of r dot cross r double dot upon mod of r dot. So, this becomes the expression for the principal normal in generalized parameter. Okay. So, all the expressions for T, N and B are available to us in natural parameter as well as generalized parameter. All right. So, expression for Frenet-Haddon I have done. The next topic that I am going to take up is the curvature of a space curve. Curvature of a curve, whether it is space curve or plane curve does not matter, of a space curve. All right. So, throughout we will assume that C is a regular space curve with natural parameter S. All right. So, the notion of curvature is known to all of us. In fact, even a layman knows what actually is the meaning of the curvedness of a curve. The only thing at this point is that we want to measure this bentness of the curve or the curvedness of a curve. How to measure the bentness at different points of the curve, this is really the idea now. So, you see, look at these curves. For example, I have this curve, then in the second stage I have this curve, then this curve, then this curve and this curve. I have drawn so many curves. Just by looking at the curve, you will say that this curve has the highest curvedness and this has more curvature than this one or this one. And if you look at the straight line, you will immediately say that its curvature must be 0. There is no curvedness in the straight line. So, you can see that if I take two neighboring points on the first curve, then you can see that the tangent over here and the tangent over here have almost the same direction, except that there is a slight deviation in the tangents in these two at these two neighboring points P and Q, but over here the deviation in the tangent will be little more. Okay. So, look at the angle between these two tangents. Here deviation is this much, and if you look at this one, deviation will be little more. This is more than this, and in the last one, the deviation in the tangent between the two neighboring points will be the highest. So, in fact, the change in the tangent really measures the bentness of the curve at a given point. So, this gives me the idea to get hold of the curvedness of a curve. I will just say that the curvature. So, let me draw only one curve over here. Suppose this is the curve C, whose equation is r equal to r s. Let me draw the two tangents at two neighboring points. So, this is the unit tangent T corresponding to the parameter S. Okay. Over here the parameter is S, and then I will draw a tangent at another point. Say this is also unit tangent, but this is drawn at a point whose parametric value is S plus H. So, both T s and T s plus h are unit tangents. Now, let me draw these two tangents over here. So, this is the tangent T s and the tangent, this is point P, this is point Q, and the tangent at Q, let me draw over here. So, this is T s plus h. The angle between them is suppose theta. Okay. So, let me write down a rough definition of the curvature. So, the curvature of a curve C at a point P, P is R s. Okay. At a point P is given by, is defined as k equal to theta upon h when h tends to 0. Okay. Now, in order to read everything, you have to refer to the figure. So, these are the figure. This is figure 1, this is figure 2. So, refer to the figure 1 and 2, refer to figure 1 and 2. What is theta? I need not write down that theta is the angle between the two neighboring tangent T s and T s plus h. H is the arc distance from P to Q. You can understand that this distance is h. Over here the parametric value is s, over here the parametric value is s plus h. So, this arc length must be h. So, this becomes my first definition, which I have written down intuitively. Okay, let me work it out little more and make it more precise. So, look at figure number 2. If I call these points as O, suppose this point is B and this point, sorry, this point is A, this point is B. Now, you join A and B. So, you get a triangle OAB. In this triangle, if I bisect the angle theta, so I am drawing the bisector of the angle theta. So, I mean that this is theta by 2 and this angle is also theta by 2. So, by elementary geometry, the two triangles OAC, it will meet somewhere with C. So, you can easily see that the triangle OAC and the triangle OBC, they are congruent to each other. Why? Because the length of OA and the length of OB equal, both are unit tangent, these two angles are equal, this side OC is common. So, by SAS, these two triangles are congruent to each other and therefore, all corresponding sides should also be equal, meaning thereby that this side AC is same as the side CB, and in other words C is the midpoint of the side AB. So, AB, the length of AB is equal to 2 times the length of AC or CB, whatever, AC. Okay. This follows from figure number 2. Okay. And moreover, now from figure 2. Moreover, this triangle is a right triangle. In fact, both of them are right triangle, okay, because this angle will be same as this angle and the whole angle is pi. So, this must be pi by 2. So, since both the triangles are right triangle, since triangle OAC and triangle OBC are right triangle, you can compute sin theta by 2 from any of these two triangles. You pick any of them, they are congruent, does not matter. So, let me pick the upper one, OAC. So, sin theta by 2 will be equal to AC upon OA. OA is the length of the unit tangent, which is 1. So, it is just AC, length AC, and length AC is in fact half of length AB. Okay. So, this is equal to half AB. If you want to write down, this will be OB minus OA, and this is half of OB is Ts plus H minus Ts. So, sin theta by 2 is this much, call it number 1. All right. Now, apply this the first definition. This is the first definition of the curvature. So, now by the box relation 1, now by box relation, now by box 1, k equal to the curvature of the curve at a point P. This is important. Curvature of a curve is not same throughout. I am computing it only at a point P. So, k equal to limit h tends to 0 theta upon, now I will multiply and divide by 2 sin theta by 2 and multiply also by 2 sin theta by 2 upon h, and the value of sin theta by 2 I will put from here. So, this 2 I can send up and it becomes sin theta by 2 like this. So, the limit of the product equal to product of the limit. So, this limit when h tends to 0, theta also tends towards 0. Look here, when the h tends to 0 means q tends towards p. When q will tends towards p, then this h will also tends towards p. So, theta will become 0 because the two tangent will coincide. So, I can replace this first limit by limit theta tends to 0, theta by 2 upon sin theta by 2, and this limit here I can write down the value of 2 sin theta by 2 from number 1. So, this become T of s plus h minus T s under modulus sign, because they are vectors, upon h, limit h tends to 0. The limit in the first term is just simply 1, and this you can recognize is it is the derivative of t with respect to s. So, I will call it t dash, okay, at the point P, or you can say S. Parametric value is S, the actual point is P. So, what do you find? You find that the curvature k, which initially we define as the rate of change of the tangent, comes out to be t dash. Okay. t dash at a point S. T dash, what is T? T is r dash. So, what will be T dash? T dash will be r double dash. So, if you like, you can also call it r double dash, okay, at the point S. So, this is another expression for curvature, and practically it is the same as we started. We were calling it as the rate of change of the tangent, and still it is the rate of tangent. We have just put it as the derivative of t. Okay. Now, at this point, you better call it curvature at a point P. All right. At this point, I can think of n. You see, this is box 2. We know that n equal to the principal normal n is in fact r double dash upon modulus of r double dash, and modulus of r double dash is now the curvature k. So, this becomes r double dash upon k. Okay. Which is okay. So, r double dash upon k is the principal normal, or I can rewrite this as r double dash equal to k times n. This is an important relation. In fact, at some point of time you will be interested in knowing the derivatives of the vectors of Rene triatom. So, this relation will be used there. Therefore, I have written it down here itself. All right. Now, next is okay. So expression for curvature and generalized parameter. If the video becomes too large, you can change it. Huh? How much time I have spent? Okay, so we can continue. So, so let me consider the curve in generalized parameter. So, r equal to say r t. T is a generalized parameter. I am considering the same curve. The only thing is the generalized parameter is introduced for that curve. What will be the expression for curvature? So, I will start from here. So, by definition, the curvature k is given by mod r double dash, or you may say that it is d by ds of r dash or t. I can write down t bar, because t is r dash, because t is r dash. So, if I differentiate t with respect to s, I will be getting r double dash. Okay. Now, this I can write down as, suppose my generalized parameter is t. So, we are using t for generalized parameter and t bar for unit tangent. So, no need of confusion. Whenever I will take unit tangent, I will put a bar. Without bar means the generalized parameter. So, this I will write down as d by dt of t bar into dt over ds. Now, unit tangent t is known to us. If you remember, unit tangent t, which is r dash, is r dot upon mod r dot. This was r dash as well. So, I will make use of this expression for t over here. So, this becomes d by dt of r dot upon mod r dot into dt upon ds is 1 upon mod r dot. All these things are known to us. So, I have to do nothing but just to differentiate it. So, we are differentiating with respect to generalized parameter. So, keep 1 upon mod r dot out, left hand side is k, 1 upon mod r dot is out. Now, let me consider the derivative of r dot upon mod r dot. Now, this I will read as if it is a quotient function. In numerator I have r dot and in denominator mod r dot. So, derivative of a quotient function is given by derivative of r dot will be r double dot, mod r dot will be kept as it is, minus r dot as it is into derivative of mod r dot upon mod r dot square, straight away by the elementary formula. So, you have outside 1 upon mod r dot cube and this quantity will be r double dot into mod r dot and this is minus r dot and this d by dt of mod r dot. Let me compute it. So, d by dt of mod r dot. What we will be doing? We will be writing it as r dot dot r dot whole to the power half, and this can be differentiated as half into r dot dot r dot whole to the power minus half into 2 times r dot dot r double dot. So, 2 goes off, it becomes r dot dot r double dot upon mod r dot. So, this comes out to be the derivative of mod r dot with respect to t. So, this is r dot dot r double dot upon mod r dot. So, mod r dot. Okay, this we have already taken out. Okay. So, let me simplify a little more. I will multiply it over here and this will become 1 upon mod r dot to the power 4 and this becomes r double dot into mod r dot square minus r dot dot r double dot into r dot. Okay. So, or 1 upon mod r dot to the power 4, this I can write down r dot dot r dot into r double dot minus r dot dot r double dot into r dot. Look at this bracket. If you recollect the expression of vector triple product, suppose A cross B cross C is the triple product of the 3 vectors A, B, C, then you remember it comes out to be A dot C into B minus A dot B into C. This is the formula for the triple product, vector triple product. So, A dot C into B, okay, and this becomes A dot B into C. Yes. So, it becomes, and modulus sign was there. modulus sign was there all along, I missed it. So, please put a modulus sign also, that was there. So, okay. So, we get it 1 upon mod r dot to the power 4 and modulus of r dot cross r double dot cross r dot. Okay. Now, apply the formula of the cross product and keep in mind that r dot is perpendicular to this bracket. This r dot cross r double dot is perpendicular to r dot as well as r double dot, and therefore, r dot is perpendicular to it. So, the angle between them is pi by 2. So, 1 upon r dot 4 and this becomes modulus of r dot cross r double dot into modulus of r dot into sin pi by 2, which is 1. So, you get this. So, 1 power is cancelled out and you get mod of r dot cross r double dot upon mod r dot cube. So, you get expression for curvature in a generalized parameter. So, let me write down that expression over here. So, in generalized parameter, curvature is given by the formula r dot cross r double dot upon modulus of r dot cube. Okay. So, I think we can stop, and we in our next lecture we will be discussing the torsion of a curve. How much time I have taken in the second lecture? 37? Okay.